All right, so this is going to be 5-2 binomial probability distributions. So let's see what we are going to learn today. So binomial probability distributions, but a binomial distribution, probability distribution results from a procedure that meets these four requirements. So this is very important. The procedure has a fixed number of trials. So whatever we do, we're going to do it a certain amount of times and that's it. It's not just randomly. The trial must be independent, meaning that the outcome of any individual trial does not affect the probability in the other trials. Each trial must have all outcomes classified into exactly two categories: success or failure. So the probability of a success remains the same in all trials. It always has to be the same. Say you want to know the probability of picking out of, let's just say this is a sack, right? And there's 5 balls. 1, 2, 3, 4, 5. Actually, instead of doing that, let's make 1 red, 1 purple. Yeah, that's what we'll do. 1 red, 1 purple, 1 blue, 1 green, and 1 black. Okay, so there's our 5 balls. Now, there's something, so if I want to know the probability of picking a red ball, we know there's only 1 red ball. Oops, there's only 1 red ball out of 5 balls. So it's 1/5, which is equal to 0.20 or 20%. Okay, so that I think we're all familiar with. Now there's something called with replacement and without replacement. So with replacement means after I pick that red ball, I put it back in and I have the same exact probability for the next time. Maybe the next time I want to know what the probability of picking blue ball. And all of them are the same, right? It's still 1/5 and so on. This is called with replacement, because after I pick the ball, I put it back in the sack, right? Now, if I pick the ball, if I wanted the probability of red, and when I picked a red, I didn't replace it. So without replacement, now every outcome is going to be different, right? Because first I pick a red ball and it's 20% or 0.2. But if I don't replace it, then I only have four balls in the bag. So now this last one, the probability of a success remains the same in all trials. That wouldn't be true. So I wanted to give you an example of when that last one wouldn't be true. Okay. Notation for binomial probability distribution: S, success, and F will denote as failure. And so those are our two possibilities. And if you think about binomial, bi means 2. So it is the probability of something or something else, right? Okay, so N is the fixed number of trials. I'm going to do this 20 times. X is a specific number of successes in N trials. So first, let's do it like this. So 20 trials. I want, in those 20 trials, I want to pick a red ball. Okay. So the, hold on. Okay, so let's say n is the number of fixed trials. Let's say I'm playing tennis, okay? So I'm going to play 5 games of tennis, okay? X is the number of successes in n trials. I want to know the probability of winning 3 games out of the 5, right? The probability of success, let's say I think I'm a better player. So I have a 60% chance or a 0.60 chance of winning. So if I have a 0.6 or a 60% chance of winning, I have a 1 minus 0.6 chance of failing or losing, right? Which is 0.40. So that's what P, so this is equal to P, and this is called Q. Okay. And then P of X is the probability of getting exactly X successes among the N trials. So I want to say the probability of 3. That's what that notation means. Now we have this formula. I really don't want to go over this formula with you too much because you're not going to use it. So there's really no point. But we already know what all these mean. This again is n factorial, which means that it's n times n minus 1 times n minus 2, all the way down till I get to 2 times 1. So again, for example, if I say 5 factorial, what I'm actually saying is 5 times 4 times 3 times 2 times 1. Okay, we went over it before, but just in case you missed that lecture, I figured I'd put it in here. And there's ways, if we were actually going to use that formula, there are ways to simplify it, but we're not going to use it. So I'm not going to bother. So I'm going to show you how to do this problem and get the correct answer. Okay, on StatCrunch. So let's do this. And StatCrunch. Okay, so it says when an adult is randomly selected with replacement, that's very important because remember, without replacement, the probability changes. That the person knows what Twitter is based on results from a Pew Research Center survey. Supposing we want to find the probability that exactly 3 of 5 randomly selected adults know what Twitter is. So here's what we're going to do. We're going to go stat calculators, and we have one that says binomial. Okay, and that's it. You don't even have to go into options because there's really nothing there. So here it's telling me that 3 of 5. So n is equal to 5. P is the probability of success. So that's the probability that the person knows what Twitter is, right? So this is 0.85. And now the probability that X, so we want exactly, so we want equals 3. So exactly 3 of 5, we hit compute. And I don't know if you can see this, but basically this right here, this number 0.13817 and so on, that is our probability, okay? What if I say, and here's a graph of it. So if I say the probability that X is less than or equal It'll be a little bit more, but it won't be a lot more, right? Because we can see from this graph, it's getting smaller and smaller over here. But if I say greater than 3, look how big that is. That's a very large number. So you can get whatever number you would like, okay? So that's basically how we do it. I might leave that open just to see if I need it again. I think I could probably, yeah. Okay, so based on a Harris poll, 60% of adults believe in the devil. Assuming that we randomly select 5 adults, okay, so N is 5 again. The probability that they believe in the devil is 0.6, 60 divided by 100. A says we want the probability that exactly 3 of the 5 adults believe in the devil. Exactly 3 of the 5. And our number is 0.346 and 0.3456, exactly, okay? So that's the answer to A. Now let's look at B. The probability that the number of adults who believe in the devil is at least 2. So basically at least 2 means 2, 3, 4, 5, right? So I can say greater than or equal to 2. And I hit compute. And that's a huge number. Is that the same number? Yep, that's exactly the same number as we have here. So this is really what you're going to use. I'll show you that under options, there's really nothing to do, okay? So everything that you can do with this binomial calculator is right here. And I mean, this is a very short section. I wanted to put this in here because we will, I don't know, I haven't found anywhere in StatCrunch to work these numbers out. So for binomial distribution, if I want to find the mean or the standard deviation or both, what we do is multiply n, which is the number of successes. Right here, n is 5, right? Times p, the probability of success. So if I wanted to know the mean of this right here, of the 60% of adults believe in the devil, we would say x, n times p. So 5 times 0.6 is 3. So that's the mean. The standard deviation is the square root of 5 times 0.6 times, remember Q was 1, oh, here it says it right here. Q is 1 minus P. So 1 minus P is 0.4. So I'd multiply 5 times 0.6 times 0.4. And then I take the square root of that, and that would give me my standard deviation. And I do have some problems ready to go. So we're going to do a couple of Pearson problems, and we will call it a short lecture for today. And I'm sure you're all very happy about that. I think I have enough information here for you to do all the homework. So, okay, number 1, assume that a procedure yields a binomial distribution with n equals 5, and the probability of success is p equals 0.50. Use a binomial probability table. We don't have to. We're going to just use our binomial calculator to find the probability that the number of successes x is exactly, so equals 4. Compute. So here is my probability. I'm going to paste it in here, and then I'm sorry, I can't do it that way. I'm still going to paste it in here. And it says round to 3 decimal places. So 1, 5, 6. I'm going to erase 2, 5 and check answer. See, that's it. Easy enough. Assume that random guesses are made for 7 multiple choice questions on an SAT test. So 7 for N. Each with the probability of success or getting it right given by P equals 0.2. Oh, that's not good, is it? I would like a better chance than that. Find the indicated probability for the number of correct answers. So this one's saying the probability that the number of correct answers is fewer than 4. Fewer than 4 means less than 4. You could even say less than or equal to 3, whichever way you like it. Hit compute, and there we have our answer. So pretty good, right? So we have a very nice probability of getting, oh, no, that's not good, of getting less than 4, 1, 2, or 3 right out of 5. That's out of 7. That's not actually excellent. So let's see, 4 decimal places, 1, 2, 3, 4. So this last 6 goes to 7 and check answer. Perfect. So this is not too bad, right? This is the one that, is this the one? Oh yeah, this is the one that I wanted to do because it's manual. So let's do this first. Okay, so it says, assume that different groups of couples use a particular method of gender selection, and each couple gives birth to one baby. This method is designed to increase the likelihood that each baby will be a girl, but assume that the method has no effect. So the probability of a girl is still 0.5. So there's basically a 50-50 chance of being a girl. Assume that the group consists of 23 couples. Okay, so this is important. This is important. And it says find the mean and the standard deviation for the number of girls in groups of 23 births. Okay, so remember the mean is equal to N times P. Here N is 23 and the probability is 0.5. So if I multiply that together, half of 23 is 11.5. So type that in and make sure we got it right. Perfect. Okay, that was pretty simple, right? Okay, next, we want to find the value of the standard deviation. And I said that the standard deviation is equal to the square root of N times P times Q. So that's equal to the square root. N is still 23. P is still 0.5. And Q is 1 minus P. So it's also 0.5. Okay. And if we multiply those all together, let me do that on my calculator. And then take the square root, I get that my standard deviation is equal to 2.39. Actually, round to 1 decimal place, that's enough, but I'll put this in. If I round to 1 decimal place, it's going to be 2.4. Perfect. Okay, so now it says use the, let me erase this first. All right. So use the range rule of thumb to find the values separating results that are significantly low or significantly high. And hopefully we remember that here in the middle, we have the mean, which is 11.5. And then from here to here is not significant. This is mu plus 2 times sigma, and this is mu minus 2 times sigma. So basically, anything less than this is significantly low. Anything greater than that is significantly high. And anything in the middle is not significant. I think we've gone over this a few times. So so this is significantly high, significantly low, and in the middle here is not significant. Okay, so now we have to figure out what those values are, right? So we have 11.5 plus 2 times 2.4. And here we have 11.5 minus 2 times 2.4. And let's see what those values are. So this is 16.3. And this is 6.7. Okay. So now let's figure out what now that we know all our numbers, let's see what the question says. Use the range rule of thumb to find the values separating results that are significantly low or significantly high. Values of blank girls or fewer are significantly low. So we said 6.7, that's on the low end. Perfect. Values of 16.3 or greater are significantly high. Perfect. Okay, so now I'm going to erase this so we can read the question. Is the result of 21 girls a result that is significantly high? Well, 21 girls is definitely greater than my cut point, which was 16.3. So the result is significantly high because 21 girls is greater than 16.3. That's our cutoff, right? For significantly high. A result of 21 girls would suggest that the method is well, let's see what the method was. Gender selection, each couple gives birth to one baby. Well, it's increasing the likelihood by a lot. So I would say is effective. We'll see if I get it right. Exactly. Okay, so it's effective because without the treatment, we have a 50% chance of a girl and a 50% chance of a boy. But with this treatment, we're getting significantly higher values. So the treatment is effective. And that really is all I have for this video. Thank you for watching, and I'll talk to you soon. Have a good one. Bye.